In this video, I'm going to solve a problem involving 2D modeling. So we're going to create a model here for this situation, and we're going to solve for some values. So what we have here is called an Atwood machine, and that's just the name for a device that has two objects connected by a rope over a pulley. And we see here we have two different masses, so I've drawn the boxes. I've exaggerated it here. Mass A is 15 kilograms, mass B is 12 kilograms, so mass A is clearly more mass. We're told to find the tension in the string and to also find the acceleration of the system when the masses are released from rest. So we can think here that someone's holding these masses, preventing them from moving, and then they release them. And we want to find these values and see what happens once it starts moving. So we're asked to find tension and also the acceleration of the system. So the first thing to do with a problem like this is to draw the free body diagrams. The reason we start there is because we want to find the forces that are acting on each individual object. When we draw the free body diagrams, that helps us then to be certain that we're accounting for all the forces that we need to think about when we're utilizing Newton's second law. So it's always good to start from the free body diagrams. So if I look at mass A, that's clearly the heavier mass. So let me draw a free body diagram for this, and I'll draw it just under here. So I start with my dot, and mass A is heavier than mass B. It has more mass. So I'm going to give it a line downward, and this is going to be the weight force. So we'll just call this W sub A. And this is going to be equal to, well, we have the mass of A times the acceleration due to gravity. So that's the weight force. And we know also that it's attached to a string, so we have some sort of tension force. And it'll be less than the weight force, because we know it's going to accelerate downwards. Once this is released from rest, because we have mass A being more massive than mass B, well, clearly mass A is going to accelerate downwards. And if mass A accelerates downwards, well, they're connected by this pulley, so then mass B must accelerate upwards. And because it's a system, because they're coupled, we know that these accelerations, even though they're pointing in different directions, they're going to be the same magnitude. So we're going to have the same magnitude of acceleration in this system. And what is connecting these two blocks with the string is then going to result in a tension force. So we have this upward tension force that's holding this mass as it falls. So this is mass A's free body diagram. It's going to be accelerating downward. It's going to have a weight force, and it's going to have a tension force on it. So now we can move to mass B. So I'm going to draw another dot for mass B. And the tension force for both of these objects is going to be identical. It's the same string. So I want to be sure my tension vectors are of equal length. So there we go. So we have this upward tension force. And now I know that the weight force of object B is going to be less than object A. It has less mass, so it's 12 kilograms compared to object A, which is 15 kilograms. So my weight force vector is going to be less than the weight force of object A, and it's going to be shorter than the tension vector. Why? Because it's accelerating upwards. If F equals ma, we have some sort of upward acceleration, so we have to have some net force in the upward direction. We have F net, which means when we subtract this weight force, which we can call WB, which is equal to the mass of B times gravity, when we subtract this from the tension force, we're still going to have some sort of force pointing upward. Otherwise, this thing wouldn't accelerate upward. So we need to ensure that the tension force is greater than the weight force pointing downward. So that's the case. Now we have both these free body diagrams. We have the free body diagram for mass A, and it has the tension force and a larger weight force pointing downward. And we have the free body diagram for object B, which has a larger tension force and a smaller weight force. So once we've reached this step, then we can write the Newton's second law equations for each object. They're all going to be in the vertical direction, so we don't have to write, for example, the sum of the forces in the x direction or the y direction. They're all in the same direction in this problem. They're all vertical, so we don't have to differentiate between horizontal and vertical forces. So we look at each one of these, and I'm going to start with mass A. So for mass A, well, what do we have? We start with Newton's second law, and we know generally the equation is the sum of the forces is equal to the mass times acceleration. So I can look at these forces here and I can add them. So this means then the sum of the forces, I have a positive tension force and I have a negative weight force. So minus the mass of A times G. So that is my sum of the forces, positive T plus a negative MAG. And this is equal to now the mass of the object, so that's MA. And here we have to be careful because we're looking for the mass of the object times acceleration. So we have m sub A. But unlike the one-dimensional problem that we've done before, here we have two different directions for acceleration. And now we have to be sure to keep account of which direction each block is moving. One is accelerating in the positive direction and the other one is accelerating in the negative direction. And in this case, that negative sign is very important. And it goes over here, so it's still accelerating as a system with a magnitude of A, but mass A is going downwards. So this is actually negative A. So we have the sum of the forces equals tension minus MA sub G, that's the weight force going downward. And then this is equal to MA. So the mass we're interested in is mass A, and the direction that's accelerating is downwards. So we want negative acceleration. Now I can solve for T because I know that both of these blocks are coupled with the tension in this rope. So this rope is going to have the same tension throughout it. And I know that both these equations will have T, so I'm going to go ahead and solve for T. So to do that, I add m sub A times G on both sides, plus m sub A times G. And tension then is equal to m sub A times G. I'm going to pull the negative sign out front, and it's going to be minus m sub A times A. So the minus sign I pulled out in front, it made this whole term negative, and so I put the positive in front, the m sub A times G, and then it's minus m sub A times A. And this is our first equation for this coupled system. And I solved it for T because I know both equation is going to have a common force of T that I can equate in a little bit. So now let's look at mass B. So mass B is the sum of the forces, once again, equals mass times acceleration. And I'm looking at mass B. So, okay, so now the sum of my forces here, I have, again, a positive tension force. And now I have a negative weight force, and it is m sub b times g. And the same as I did in this top case, now I have to look at the mass I need because this is equal to ma, but now it's a different mass. So this is the mass b. And now which direction is the acceleration pointing? Now the acceleration is pointing in the upward direction. So now we can just write a positive a. For the other object, it was accelerating downward, so it needed a negative sign. And now I once again can solve for t because they're both going to have t as a common force. So I'm going to add m sub b times g to both sides. I'm just adding that to both sides. And I have t is equal to m sub b times a plus m sub b times g. And that's it. I found those two equations for the two objects, and now we can set them equal to each other. And the reason we want to do that is because I can then solve for a. A is unknown at this point. We don't know what a is. We know what g is. We know what the masses are, but a is unknown. And t is also unknown, but I can get rid of t because I can say, well, this one's equal to t, and this second one's equal to t, so they're equal to each other. That gets rid of this factor, this value of t that we're unsure of, and it only leaves one unknown. So when I set these equal to each other, I'm first going to write this right-hand side of the first equation and then the right-hand side of the second equation. So it's going to look like this. So I'm going to have m sub a times g minus m sub a times a. So that is this portion right here. And since they're both equal to t, I'm now going to write this portion right here. And that's m sub b times a plus m sub b times g. And I'm wanting to get this acceleration. It's buried in both of these terms here. I want to get them both on the left-hand side. So what I'm going to do to get a by itself is subtract m sub b times a from both sides. So minus m sub b times a. And I'm going to subtract m sub a times g from both sides. And we'll see what will happen here in just a second. So minus m sub a times g. So let's see. These two, this is a positive and a negative, so that's 0. And I have a positive and a negative, so that's 0. And so now I can combine everything and see what I have here. So I have a minus m sub a times a minus an m sub b times a, and that's equal to a positive m sub b times g minus an m sub a times g. And I can multiply both sides by -1. So I can, let me shift this up a little bit. So I see this negative minus sign here. I can multiply both sides by -1. So -1 and -1. And this then becomes positive m sub a times a plus an m sub b times a. And this is equal then to a positive m sub a times g and a negative m sub b times g. And now I can bring the factor of a outside of the parentheses. So I can factor out this factor of a, and I have a times the quantity m sub a plus m sub b is equal to, and I'm going to also factor out g, so then I'm going to have g times m sub a minus m sub b. And I'm very close to having a by itself. I'm now just going to divide both sides by the quantity m sub a plus m sub b. And m sub a plus m sub b over itself is 1. And then I have the acceleration is equal to the acceleration due to gravity times the quantity m sub a minus m sub b over m sub a plus m sub b. And that was complicated, but we have every single one of these values. We know what g is. That's 9.81 meters per second squared. And we know what each one of these masses are. So I can actually write out these values. I have 9.81 meters per second squared is g. And the mass of A, if we look up here again, the mass of A was 15 kilograms, and the mass of B is 12 kilograms. So writing that here, we have 15 kilograms minus 12 kilograms over 15 kilograms plus 12 kilograms. And so I can simplify this further. I have 9.81 meters per second squared. And the top is 15 kilograms minus 12 kilograms. Well, that is 3 kilograms. And the denominator here, we have 15 kilograms plus 12 kilograms. That is 27 kilograms. And I can plug all this into my calculator. So I will have 9.81 times 3 divided by 27. And the value I get is 1.09. And remember, what was this? This was acceleration. So this is meters per second squared. We see the kilograms divide out, so that's good. And the value for A now I have equal to 1.09 meters per second squared. And that is the acceleration. And the last thing I'll do quickly here is I'm going to solve for this tension just to show now that we found the acceleration. So the tension is equal to the mass of B was 12 kilograms. And now we know the acceleration. So the acceleration is 1.09 meters per second squared. And then we have the mass of B yet again. And I just want to point out that I can use either of these tension equations because the tension's the same in both of them. So I'm just using this bottom equation. So we have now the mass of B once again is 12 kilograms. I'm just following the formula now. And we have this multiplied by gravity, which is 9.81 meters per second squared. So I can plug this into my calculator exactly as it is. It'll take care of the order of operations. So I have a 12 times a 1.09 plus 12 times 9.81. And the value it gives me is, this is going to be in newtons because it's kilograms meters per second squared. So the tension in the string is equal to 130.8 newtons. And that is the tension in the string. So from all of that, we were able to find individual specific equations that describe the behavior of each one of the blocks. We were able to equate those equations using a common force that is coupling the system, which is tension. And with that, we could find the acceleration of the system and also the tension that was in the string. Thanks for watching.